So you've learned about descriptive statistics and inferential statistics, but notice it's always been about one variable, right? It's one quantity that we were looking at, right? What is the mean of people's height? Maybe sometimes it's like, is the mean of this group bigger than that group, right? But it's always just been one variable. Now we're going to look at how can, like, let's look at things that are related, right? Big example, human height and human weight. People who are taller tend to be heavier, but not everybody who's 6 feet tall weighs the same amount, right? And you probably know somebody in your life that's shorter than you, but heavier than you, right? So there's something called a correlation, but it's not necessarily a one-to-one situation. So we're going to learn a small amount about correlation and regression. This chapter has a lot of sections. We are just focusing on sections 1 and 2, and they're both fairly straightforward, right? So I think this stuff is actually pretty easy. Oh, I should have the word calculate. So we're going to calculate something called lowercase r, and then you're going to explain it. We're going to use scatter plots. Do you remember that we made a scatter plot very, very early in this class for that one assignment, right? So we're going to come back to that, and we'll determine if there's a correlation between two variables. So what is correlation, right? A correlation exists between two variables when the value of one variable are somehow associated with the values of the other variable, right? You want to be careful to say that correlation is not implied that causation, right? So a lot of times, remember we actually had an example, right, where we showed, do you remember the example about the ice cream and the number of drowning deaths? Yeah, the ice cream consumption. Do you remember it seemed that the ice cream consumption caused the number of drowning deaths? What was actually going on there? Anyone remember? It was summertime, so high temperatures. So temperature was the kind of lurking variable. It caused both of them, right? So you could have something where X causes both Y and Z, right? And then that means that Y and Z have a relationship, right? So we're just looking at a correlation between two things, right? We don't know about causation, and we're just not going, that's something that's much harder to figure out, and we're just not going to talk about that, right? It's just beyond what we can do in one day. So a correlation means that two variables are correlated with each other, right? A linear correlation means that the correlation is line. Well, let's see. What is the word linear? Everyone, we know this. This is line-like, right? And so we are going to look at only linear relationships, which means they have a straight line pattern. So what do you notice about these dots? Yeah. Yeah, they seem to follow a line, right? Like you can see that these two regions, there's not meeting points in there at all, right? And specifically, right, where would you predict as if I increase X, what do you expect to happen to Y? Increases as well, right? So this is called a positive linear correlation, right? Where an increase in one variable corresponds to an increase in the other variable, right? Does everyone see that here? So that is called a positive linear correlation. I want to find my slide notes here. Now, here it is. There is also something called a negative correlation, right? So the first thing might be a height and weight type situation, right? This one is not, right? This is something that has a negative correlation. So notice an increase in X results in a decrease in Y. Does everyone see this? Now, we'll talk about this later. Which one of these would you say has a stronger linear correlation, A or B? B, right? And notice this number here, R, we're going to come back to this. The size of that R, ignoring the sign, right, tells you how strong that correlation is. So notice this is about 0.86. This is 9.7, well, negative 9.7. The negative means it's going down. We'll get to that, but that tells you the strength of it. Now this one, how would you describe these dots? There's no correlation, right? I'm not very athletic. I know, shocking, right? Or very coordinated. I'm more athletic than I'm coordinated, which really shows you that I'm not coordinated at all, right? This looks like I'm throwing darts at this, trying to, right? Like there's no correlation at all, right? So that is what we call null correlation, right? Now, is there a correlation here? They're a strong, very strong correlation. They all are following a pattern that looks like it's a trajectory of an object, right? So this is a strong correlation, but the correlation, does it follow a straight line? No, right? So what we're going to be doing is only able to find linear correlations. So as far as we're concerned, this is the same as the previous one. It's not, right? But we're just not going to talk about it, right? You're interested, there are other things. Okay. So what is the linear correlation coefficient, right? So it is some value, and it's called R. It's lowercase, but this is all caps, so it made it cap there, right? It tells you the strengths between paired quantitative values of X and Y in a sample. Obviously, I mean, it could be a population if you happen to have data from the whole population, right? But you typically don't. R, and their formula, R will always be a number between -1 and 1, okay? -1, R equaling -1 would refer to a perfect linear, negative linear relationship. So the negative means that the line would have a negative slope, okay? And what would be a perfect linear relationship? That would mean all the points fall on a, yeah, right? So here's a negative linear relationship. You can see that the trend is pretty strong, but they don't, do all these points fall on, is there a line that I could draw that all of these points would fall on? What do we think, everybody? No, right? Now we can follow the general trend. So notice this, the closer, when you're looking at a negative trend, right? This number is fairly close to -1, which means you have a very strong negative linear correlation. This one has an R value that's positive, and it's close-ish to 1, but definitely not as close as the other one was to -1, right? This has almost no correlation, right? So R is almost equal to 0. Okay. That's weird. Right, the size of R tells the strength, right? The sign of R says whether it's a negative or a positive trend. Okay, so requirements is that your samples have to be paired in a meaningful way. So if I collected height and weight from everybody in this class, those data would be paired in a meaningful way, right? If someone, like for example, I'm probably lying a little bit here, but I'm 6 feet tall. So let's just make it inches, 72 inches, right? I weigh about 210 pounds. That is a pairing of data, right? The 72 and the 210 are associated with me, right? Now, Let's say I collect, I don't know. Let's say I have, let's say here's Illinois, here's Indiana, right? And then in each of them, I go to 8 warehouses, right? And I count how many boxes are in each warehouse, right? I could have 8 sets of paired data, but would that be a good idea? So paired data is my weight and my height. But in this case, I'm saying I'm going to Illinois. I'm going to look at 10 warehouses. Look at the same number of warehouses in Indiana. I'm going to look at the number of boxes in each, right? So I might have a paired data. 20 boxes in warehouse 1 in Illinois and 81 in warehouse 1 in Indiana. Does that make any sense? Say that again?
Know that it's for what it corresponds to, but if like if you're plotting that on the graph, those looks like
Are these numbers, is the pairing of 820 with 81 like, is it a meaningful pairing? I know, guys, these error houses are arbitrarily numbered from 1 to 10, right? We following? So this is not paired data because the two pieces of data are not associated with each other, right? It's arbitrary. So for paired data, you want data that is meaningfully paired, right? So in this case, this is my height. This is my weight, right? I could do Regina's height and her weight as another data pair, right? They need to be paired, right? Like you can't just make the pairing arbitrary. There's no reason to do that, right? Now, for R to be valid, right? So this is what these requirements, right? These are requirements for R to be a meaningful value, right? And remember, R is supposed to tell us the strength of the linear relationship between two variables, right? So one, you want to graph the two things to see if they have a straight line pattern, right? Otherwise, you might be missing something. For example, this one has an R value of 0.33. That implies that there's a positive linear correlation, but it's just a weak one. Is that true? There are linear correlation between X and Y here, ladies and gentlemen. No, there's a very strong correlation of a nonlinear type, right? So you don't want to use R to rank how strong your correlation is if you look at the graph and there's not a linear correlation in the first place, right? What's the other thing? I don't know what's going on with people just leaving the room now. The other thing is this. R is not accurate if there are a lot of outliers, right? So let me just create a graph here for you. Is there a strong linear correlation here, ladies and gentlemen? What do we think? No, right? Now, still no, but now you might get a decent R value because, hey, there's that line. It explains some of the trend, right? Or at least appears to, but it's really just that there are two different scatter plots, each of which has no linear correlation, right? So if you have one outlier or a couple of outliers, it can make R larger than it should be, right? So in a case like this, you should calculate R with this and without this. And unless both of them are decent, right, you should conclude that there's no linear relationship. All right. All right. So the question naturally about R is then what? Well, I've told you what it means. Yeah, how to find it, right? So you'd probably like a formula. Ready? All right, here's the formula that you use to calculate R. It's not, it's very cumbersome, but let me just tell you what it means, like a little bit, all right? So this XY, this means the sum, right? So there's a set of parents, right? And, like there's an X coordinate and a Y coordinate. So in that case, I'd multiply my height and weight, right? I'd multiply all those. I would sum those up, multiply that by N, the number of pieces of data, right? Then I would also sum up all my X's individually and sum up all my Y's individually and then multiply those two sums. Do we get that that's different than having each of the products and then adding them together, right? It's not the same thing. And then this right here is adding up the squares of all the values. This one right here is adding up the values and then squaring, right? It's a different order. Okay, now the good thing is I'm not going to ever ask you to do this, right? Like, do y'all remember when I had you calculate standard deviation by hand? Yeah, that was pretty tedious, right? So this is going to be even more tedious and more likely for you to make a mistake, right? But it's just but you all could do this if I spent enough time on it. It's just a waste of your time. Okay, so I am going to show you how to calculate this, right? In your graphing calculator, but not right now because I want to give it for a meaningful thing, all right? So one is how you calculate R, and two is how do you calculate which line is the best fit line? So let's learn some properties, and then we'll learn how to calculate it, and then we'll make some sense of it, all right? Oops, I'm way out of line here. Okay. Here are some important properties of R. Now, it might make sense to you to think of, hey, a person's weight depends on their height as opposed to the other way around, because we think of as weight as something that we have more control over than our height. And I guess we do, right? But mathematically, it's no different. We don't know, right? So if I switched, right? If I did, let's make X height and Y weight, right? Or I could switch it around, all right? Either way, I'm going to have the same value of R, right? Which makes sense. It should be, because R measures how correlated how correlated in a linear fashion are these two variables, right? It shouldn't matter which one we examine first to determine that. Do we all agree? The other thing that shouldn't matter is how those things are measured, right? If we measure height in inches or feet, it's not like, hey, a person's weight is strongly dependent on their height in inches, but not at all dependent on their height in feet. That doesn't make any, you see how that's a nonsensical thing to say. So it does not matter, right? It is, again, a strength of a linear relationship. You could have things that are very strongly correlated, but if that correlation is not linear, it's not going to measure that, right? It's going to give you an incorrect thing. And we saw that for that curved graph, that parabolic graph. And it can be very sensitive to outliers, right? even a single outlier. So if you have one data that's much, much bigger, right, then the other one you should calculate R with both with that outlier and without it. Okay, so let's take this moment to fish out a couple of different things. So fish out your table. We've used now all pages except for the last one. So today we will use the last page on this table, right? And fish out your graphing calculator, all right? Okay, so let's start by looking at our graphing calculator here. Don't look at this. Just ignore what's going on right now. So I don't know who decided to design graphing calculators this way, but it doesn't make any sense. So there's a way you can calculate R in your graphing calculator, but there's a setting that makes it like not do it correctly. Or actually it doesn't make it not do it correctly, it makes it not show it, which is really weird, right? So I'm going to teach you how to. Okay, so what you're going to do is you're going to hit second. And then notice where it says 0, there's the word catalog above it, right? You're going to hit catalog. And this is literally the catalog of everything that's in your calculator, okay? Now, I just need you to follow along with me once, okay? So you can scroll all the way down until you get to the D's. You're going to get to something called diagnostic on. Everyone got there? Then you're going to press enter. Then you're going to hit enter again, and it's going to say that it's done. That's weird, okay? Now, once you've done this, R will be calculated correctly, all right? However, the cool thing is you don't have to do it again, except what I make you do before every celebration. Yes, you have to do it once, and I will, since this isn't something you do repeatedly, I will remind you and demonstrate doing this, okay? So you don't have to remember this, right? You'll see what happens if that was not on, okay? So then we want to move forward. So has everyone successfully turned their diagnostics on? All right. So anyone here ever work waiter or waitstaff job here? No one has. Wow, usually there's somebody, all right? So hopefully, right, we know that there's an expectation about how much you're supposed to tip in America, 20%, 15%, depends who you ask. I think it's 20, right? So there should be a correlation between the quantities, right? How much you tip and how much the bill is, right? We would expect there to be a linear correlation, right? Do we all agree with that? Okay, so we have to see if there is one. So let's do that. Let's go back to our account. So here's our data, right? Our bill and our tip. So let's go to our data and put it into our calculator. So you're going to finally start doing some stuff that we didn't do before. So I'm going to go to edit. So I press stat, edit, and this is where I type in my list, right? So if you have something already in your lists, you might want to do second memory for clear all lists. I'm going to do stat and then edit, right? Now, for the first time, I'm going to use two of my lists simultaneously. Hopefully, we're all paying attention, okay? So I'm going to put in 33. So these right here are the 6 dinner bills, right? Now I want to enter in the amount tipped. Okay. You have trouble seeing it? Here again is the data, right? Now, it's not important the order of the data, but it's important that they're in the same order, right? I could mix these up, but I would, if I like move that, say that 107, right, to the front, I'd also need to move the 16 to the front. Everyone following, right? Because these are data that are paired. But it doesn't matter what order I put them in as long as the pairing is consistent. Does everyone understand what I'm saying here? Okay, so we need to create a scatter plot of your data. So let me show you how to do that. Let's make sure there's nothing in your y equals. So I'll come around and help you if you have trouble. Has everyone been able to get their data in there? This is not the first time we've done this, correct? So I want you to press second. It's okay if you're not on the screen right now. Stat plot. I want you to hit enter, and you want to have this plot on. Notice here, it says that my x values will be L1, my y values will be L2. That's how we have it. You can change that if you need it to, right? And look, it's also on the type is a stat is the scatter plot, right? But you need to turn this thing on. All right. Now that I've turned my scatter plot on, your datas aren't matching up there. You have to 16. You need to type 16, and you see that you don't have the same number of data. Just type in the number 16 right now, 16. There you go. Yeah. Okay. Right. You should. Yes. Stat plot. See, it literally says the word statistics plot. You want to have, notice this thing right here looks like a scatter plot. That's what we want. We need to turn it on, and then L1, L2, okay? Now, if you press the graph button, it should show you your scatter plot. Except, where is it? Correct. Now, instead of using the zoom function, which you have to keep, it's like it's not zoom friendly, right? So instead, we want to learn about the zoom, right? So everyone, notice next to y equals, it says the word window, right? Press that button. It now is telling us the window, right? So this tells you the smallest x you can see is -10, the largest is +10, right? It also says this x scale, that means that there's a hash mark, everyone. Is everyone following along? Guys, how did I get to the window? I pressed the button that says window on the top row. Is everyone here? Do we understand what scale means? Having people that aren't even looking at me right now, right? Not good. Okay, so we need to construct, let's look at our data, right? Let's think about this. Some you just need to be able to figure out, you need a window that sees all of your data, right? So our smallest data is around, let's look at x, right? For x, we need a window for x. So what's our smallest x? Yeah. And everybody, our largest y is everybody. All right. So you don't want it to be like right there because then it'll be like on the edge. And like nice numbers are nice, right? So let's go from 30 to 110. All right. And then we could say that for y, it'd be from 4 to, let's say, well, this is small enough. Let's just do 0 to 20, all right? Does everyone understand how I chose these numbers? I'm choosing a window that's big enough to see everything. They should be fairly intuitive. Okay, so now let's go back to our calculator. Let's do that. So I said 30 to 110. Zero, 20. Now, the scale is going to give me a hash mark every one, right? That's not a good scale. It's not the hugest deal because the hash marks aren't that important. But 80 hash marks is too many, right, to see. So let's make my scale maybe, let's say 4. Say that again. X scale, Y scale. It says it right here. Yes. 80 is too many, right? This is the X scale, right? This is the window. The window is going, so scale means hash mark every one, right? And our scale is from 30 to 110. That'd be 80 hash marks. Yeah, that's what I'm thinking. Counting by fours would be nicer, okay? Yeah. Yes. It's not the most important thing, but it's better to see this. We can count by one, right? So like having about 20 hash marks is a reasonable number, right? You can have fewer. Now we hit graph. And there you go. That's our graph, right? Now you can see the hash marks here. You can see the data points there. If you hit trace, you see the trace button right here? You can jump around and it will tell you the exact values of each of your points that you entered. It might seem like it's visiting them in an arbitrary order. That's just the order that you type them in. And everyone able to do that? Is anyone stuck? So I'm happy to come over to your calculator and help you. I want to make sure you know what you're doing here because this is important. Okay. So we've done that. We've constructed a scatter plot of the data. We can kind of do a brief sketch of it. Guys, I'm going to ask you to sketch, and I'm going to want mod better than like what I'm doing here. So when you are supposed to sketch it, put in your scales, etc. Everything that's good about, you know, having a nice scale. Okay. Now we need to learn how to calculate R with our calculator, okay? So there's 2 ways to do R. I'm going to show you the first way now. So again, this is statistics. So I'm going to press stat. And which menu do you think is going to help us calculate R? Calc. Okay, so you're going to scroll down until you get to option 4, which is linear regression, all right? I'm going to give you some information, right? Here's what would happen, all right? So notice we did this to calculate R. Just a reminder, I hit stat. It's going to be here for a while. Calc 4, boom, okay? We got to this menu here, all right? If you had not turned your diagnostics on, neither of these last 2 values would have been there, okay? So if you ever get this and there's no R there, that means go back to turning on the diagnostics on. Just don't clear your calculator until the celebration. You're not going to lose this, all right? Your calculator's already set up to do this. And I will say, everyone clear your calculators, and then I will demonstrate underneath the document camera turning on the diagnostics again, okay? So we got our R value. We got a 0.828 roughly. So is that a good value of R, a poor value of R, or like it's decent? And the fact that it's positive means we have what sort of correlation? Positive, which means an increase in Bill causes an increase in, or causes isn't necessarily true, right? It does in this case, but it means correlated with, right? So this is strong-ish, but Okay, my pen is all messed up, right? Sorry, don't just bear with me on that. See, look at the tip. It's all. I need to buy new ones, right? I pushed too hard. Okay, so now so a lot of the times, right? Remember in our hypothesis testing was always like, hey, our mean is higher than we think it's commonly held to be. But could that happen by chance, right? So this is kind of the idea. Is it possible that the data is not actually correlated, but this happened by chance? And the answer is, you think no, right? We need a systematic way, right? If my correlation coefficient was about 0.4, you might be like, right? So let's look at that. So there is something called finding the p-value. Okay, so there's two ways to do this, right? So I'm going to you can make conclusions with your calculator or with the table, right? There's always two ways to do it, right? Everything that I've shown you with these tables, everything that you can do with these tables, I think everything you can also do with the calculator. We're going to do the calculator first. So notice it did not give me a p-value, right? Let me show you how to find the p-value. So I'm going to do some similar second stat. Sorry, it's just stat. Go to tests. Right, we used a lot of this, right? We've done some of these for the hypothesis testing, right? Sorry, I'm a calc. You're going to scroll all the way down until you get to something, option E, linear reg t-test. So everyone got here? I'm happy to help anyone if you didn't get it. Okay. So then this is checking, right? The nice thing, okay. This one, it's like a hypothesis test. Don't ever, I don't exactly understand. Someone who's smarter than me could tell me what it means to have less or greater than, right? So basically, every time you're seeing if there's a linear regression, your null hypothesis is there's no linear regression, okay? Or sorry, there's no linear correlation. So keep that thing on not equals 0, never change it, all right? This is just saying x is in L1, y is in L2. Then hit calculate. Notice it gave us a p-value here, right? Also scroll down. It also gave us an R value, right? So there's two ways to calculate the R value. There's the way that I just showed you, and there's the previous way. So let's write down this p-value, which is about 0.41. Now before, if the p, remember when we did the p-value testing for hypothesis testing, if p was less than the significance level, what did we do? We accept the null hypothesis or reject it. Reject. So in this case, p is less than alpha. All right, so we reject the null hypothesis, right? Which means that there is or there is not a correlation. There is, right? Because the null hypothesis is always no effect, right? Yes, none, right? So that means that there is a linear correlation, right? Or the evidence, I guess we don't know that there is, but you can say that the evidence supports that there's a linear correlation. Okay. Just, you know what it says there. Okay. Now let me show you how you do that with your table, okay? Can we go to the last table in your packet? It should look like this. If you have trouble reading the numbers here, that's okay, right? We can read that up there, all right? So what is n in this case? N is the number of pairs, right? Pieces of data. So what is n for our particular, this example one? How many pieces of data did we use? No, we don't for this one because it figures that in. So notice that n in this case was 6, right? There were 6 pieces of data. You just count them. N is 6. And they're saying let's use a significance level of 0.05. So that means that's the critical value, right? So this means that R critical equals this. Does everyone understand how I found the critical value? I just look at how much data I have and what my coefficient was. So I look there. Why did this disappear? Why did everything disappear? Oh, no, it's because I was looking at the wrong one. Okay, so in this case, I find my R crit is equal to 8.1. 1, right? My R crit is smaller than R, right? So what this critical value is saying is that with only 6 pieces of data, I need an R coefficient of 0.811 to conclude that I have a 5% or less chance of this linear relationship that is there happening by chance. So since R crit is there, that means same thing we had here, reject. H naught, which means that there is a well, evidence supports there is a correlation, right? Now, everybody, if everyone were to tip the same percentage, what would R be? Everybody, R measures what? The strength of a correlation, right? If everyone tipped the same percent, what would R be? High, right? But yes. What is R always between, everybody? It's not. It's between -1 and 1. If everyone were to tip the same percentage, what would R equal? 1, because that would mean you have a positive perfect linear correlation, right? Don't want to type that out. Okay. There's another example. I'm not sure I'm going to have time to do it. Okay. On this, I will send a video of the other example. Okay. So you can watch that if you would like. Now we will take a 3-minute break and then we will spend the remainder of class finishing up the second half of this lesson. All right. Which is on regression. Yes.